Hey everybody, this is our fifth and final type of reaction that we're going to talk about in this chapter, and it's known as the double displacement reaction. Now what makes this double displacement reaction unique is that it has two ionic substances that are usually starting out as aqueous. You have A, B, and CD. And what happens is that we have the A, which is a cation, switch places with the C, which is also a cation. And so you've got the double displacement. A switches with C, and C takes A's place, and A takes C's place. So your products are AD and CB. Now in this type of reaction, it's also possible that the reaction does not occur. And I'll talk more about that in a little bit. And like I have for each one of the videos so far this chapter, I'm going to splice in a bit of information from another video that I made from another chemistry course. Now what makes this predicting products a little bit different than single displacement is you can't decide right away if the reaction happens or not. It's actually something that you decide at the end. So you may do all of this work and then at the end decide this reaction does not occur. That's kind of the sticky point of double displacement reactions, and what gives people a bad attitude towards them is because you did all this work just to result in nothing. So let's talk about the mechanism, or how the double displacement occurs. So let's take the general form of my reaction, once again A, B, and CD, and this time I'm going to predict the products, and this is how you do it. You take the outsides and put them together. So this is kind of like the FOIL system in algebra, with the first, outsides, insides, last. Well, what we're going to do is we're going to take the outsides, the A plus the D together. Now A is the cation and D is the anion, and so they need to stay in that order, A first and D last. And then I'm going to take that and separate it between the insides, so the outsides with the insides. And this time I'm going to put B with C, or in other words, C with B. Now the reason C is before B is, again, because C was a cation here and it needs to be listed first, and B is an anion, so it needs to be listed second. So that's the mechanism. You take the outsides and put them together, and you take the insides and put them together. So the way I would describe this in text is you take and pair up one of each of the outside and one of each of the inside ions. And so you may have multiples of A or multiples of B, but you just take one of A and one of D and put them together. And you take one of C and one of B and put them together. So you pair up one of each of the outside ions and the inside ions, put the cation before the anion, and balance the charges. Here's an example that I'm going to use to explain this. I'm going to start with NaOH and MgCl2. So I'm going to take Na and combine it with Cl. So take one of each, NaCl, and then I'm going to take Mg and combine it with OH, making sure that the cation's first and the anion second. I'm going to do a quick balance of charges. +1, -1, so those are good. +2, -1. So I need to take 2 of the hydroxides for every 1 magnesium. And then I go in and erase the charges. So in that order, I pair up the outsides, pair up the insides, and then balance charges. Step 4 is where you're going to determine whether or not the reaction happens or not. And you're going to need to use another tool called the solubility table. Now the word solubility is a vocabulary word, and it means will or will not dissolve. So you're checking your products to determine whether or not NaCl or MgOH2 will dissolve or not. You need, as I mentioned, a tool in order to do this, and it's called the solubility table. Now you might be asking yourself, how do I know if something dissolves or something doesn't dissolve? And we've got this table that is located on the back of your periodic table that will help us to determine whether or not our two products are soluble or insoluble. Now if you take a look at the solubility table, we have a list of soluble ionic compounds listed by anion. So in other words, if the anion ends as an NO3, C2H3O2, ClO3, etc., then these are all soluble. So we've got nitrate, acetate, chlorate, chloride, bromide, iodide, and sulfate. These are all soluble ionic substances. Now on the right-hand column here, we have important exceptions, or in other words, it will be insoluble if it's combined with these cations. Now for the first three, we've got nitrate, acetate, and chlorate. There are no exceptions. All of them will dissolve. That's what soluble means, will dissolve. Now chloride, bromide, and iodide have these 3 exceptions. So if it's silver chloride, mercury chloride, or lead chloride, then it will not dissolve. And for sulfate, we've got a couple of more. So for the most part, if it ends in one of these anions, it will dissolve. except for a few of these. Now the bottom has insoluble ionic compounds. So these anions almost always don't dissolve. That's what insoluble means, does not dissolve. But there are some important exceptions. So the exceptions to the insoluble compounds are things that are soluble. So if you have sulfide, carbonate, phosphate, hydroxide, or oxide, they're typically going to be insoluble, except if it's lithium sulfide or sodium sulfide or potassium sulfide. I think you get the idea. This is a table that helps us to determine if something is soluble or not soluble, and you will have access to this on all quizzes and tests to help you determine the outcomes of your double displacement reactions. So here's how this table works. I find my two ions, sodium and chlorine. Now I take my solubility rules and I find out that sodium chloride is soluble, so I'll label it with an AQ for aqueous. Now I'm going to do the same thing for magnesium hydroxide, and I find that magnesium hydroxide is insoluble because magnesium is not one of the exceptions that would allow hydroxides to be soluble. When it comes to determining whether or not this reaction will happen, there are really two outcomes. They will either both be aqueous. In that case, there is no reaction because essentially you have two solutions that both dissolve, so you won't observe a precipitate forming. There's no gas, there's no light, there's no heat, there's no clue that a reaction happened. If both products are soluble, or in other words, both are aqueous, then no reaction occurs. Now the other outcome is one is soluble and one is insoluble. And if that happens, you get one product that's aqueous and one product that's solid, like in this example, aqueous and solid, then that means the reaction has occurred. So it's not until the very end when you decide whether or not the reaction has happened. You do all the work. You pair up the outsides, you pair up the insides, you balance the charges, and you do all this determining of solubility. And only once you've done all that work, then you can determine whether or not the reaction will happen or not. If the reaction doesn't happen, then you would write NR. And if the reaction happens, well, then you just leave the products as they're written. You did all the work, so you don't have to do any more. But let's just say these two products were both aqueous, then you just simply go up here and write NR over the top for no reaction. Now you've seen an example of how I switch the ions, I check and balance the charges of the two products, and then finally I check the solubility rules to see if one of the two products is not soluble. And my example that I have up here, aluminum chloride reacts with sodium phosphate to produce aluminum phosphate and sodium chloride. And sodium chloride is aqueous, whereas aluminum phosphate is not, which is why I identify S for solid here as my precipitate. Now, if you look at the following list of things that could occur, and I talked about this on that last piece of the video, and I only showed you an example of one where a solid or a precipitate forms. And this is certainly the most common situation, but there are two other situations, consider them special cases, where it's possible that a double displacement reaction happens even though a solid isn't produced. The first one would be if a gas is produced, and the second is if water is produced. And this is specifically when you mix an acid, which has a substance that begins with an H, and then a base, which is a substance that ends in an OH. If you mix those two together, you're going to produce water as one of the products, and that means the double displacement reaction does happen. Now I summarized here on the bottom how you determine whether or not the reaction happens, and if both of your products are soluble, in other words, they will dissolve, then no reaction occurs. But if one is insoluble and one is soluble, then the reaction will happen. I'd like to take an opportunity to show you one more example so that you have a couple to look at in your notes. Here's the setup of this problem. We've got aqueous potassium nitrate reacts with aqueous lithium carbonate, and we need to figure out what the products are and whether or not the two products will dissolve or not dissolve. So let's first start with aqueous potassium nitrate. Well, potassium is a +1 charge ion, it's K plus 1, and nitrate is NO3, which is also a -1 or 1- charge ion. And so those combine together to become KNO3, and I'll put a little AQ here after it. Now it reacts with aqueous lithium carbonate. Now lithium is a 1+, and carbonate is CO3 with a 2-. And so I need to balance the charges, and I need 2 lithiums for every carbonate in order to have the balanced charges, and this is also aqueous, so I'll put a little AQ. Now I'm going to take the first and the last and put them together. I'm going to take the A and the D, and put them together. And so I'm going to have K and CO3. Now K is a +1 charge ion and CO3 is a 2-. And so I'm going to need 2 potassiums for every carbonate. And now I can erase those charges because we don't want to include the charges once the compound's formula has been written. And the other substance is going to be lithium with nitrate. Now lithium is a +1 charge ion and nitrate is a -1 charge ion. And so those are equal but opposite, so I just have the LiNO3. Now I check both of these products to see if they're soluble. And I look on my sheet and I see that carbonates are typically insoluble except for potassium. So that means this is aqueous. I'll put a little AQ underneath. And the next one is lithium nitrate. And I look up on my sheet, it's the top one. Nitrates are all soluble, which means they dissolve. So this one is also aqueous. And so when you've got 2 products that are both soluble and both aqueous, then you simply just need to say that no reaction occurs, and that is the end of this problem. Now I will add that if the reaction does occur and you decide that one of these is soluble and one is insoluble, then you would have to go back and balance the whole reaction. Right now this is an unbalanced skeleton reaction, but we only need the skeleton reaction in order to determine whether or not the products are soluble or not. Because they're both soluble and no reaction occurs, I do not need to worry about balancing this reaction. And that takes care of this example of a double displacement. Hopefully now you have a better understanding of how to predict products of double displacement reactions. And, as you know, that takes care of this video lesson. Thanks for watching.